Hello everyone, should we start or should we wait for some time? Is my voice coming through? Great, great. So you can so are you guys able to go through your assignments? Are you able to attempt or are you stuck at some point? Some of you are doing pretty good with assignments and others are not getting much time. Some of us haven't got the much time to finish the assignment. All right, great. So yeah, so let me also turn this thing off. All right. So should we start? Do you have any questions before we start? Yeah. So do you have any questions before we start? So H-based assignment is based on our discussion here. So in H-base, if you okay, so all right, let me open the H-base assignment. So here, not here, H-base assignment is the website. Alright, so here we have so here is H-based question. So the question is very simple. At least in description the question is very simple. If you have to design a simple Gmail like email storage and you have to store the data in H-base, what will be your general schema? What will be the table? What will be the tables? How many tables would be there? Will there be, and how are you going to decide upon row keys? What will be the columns and what would cell contains and what will be the versions? Okay, so I want to see your understanding of HBase and how have you I mean on what basis you will decide upon various tables and fields. All right, so that's the question. All right, so is the question clear to all? This is H-base assignment. We are talking about H-base assignment. Okay, it's a fairly theoretical assignment, but what you have to decide upon is an architecture of email storage, and this will definitely help you understand why did we have edge space the way it is. Okay. All right, and it's very common question during the big data interviews, by the way, and people like to ask such questions during those interviews. All right. Anybody else? Any other questions to me? Should we continue our discussion? All right. So here we are. So last date of assignment is before you, I mean, you, as soon as course finishes, within 1 week of course finish, you have to submit all assignments, and within 2 weeks of course finish, you will have to submit the project, and then you get the certificate. So you can see on the website, under your course detail, you will see the dates for various things. Alright, so we'll stick to that date. Okay, so in the last session we talked about machine learning, and so we showed you a demo of Mario in the last session. So those who attended the session, they can understand that. So a quick question to all in the okay, based on the question is, in the Super Mario game, the algorithm for successful gameplay was written by who? Meaning, who wrote the algorithm of playing Mario game? So somebody wrote the whole game engine, the Mario engine, which we used to play in childhood. And in the last demo, we were showing you the Mario playing the game. Who was actually playing? Who wrote that algorithm to play the game? Meaning, when there is a Goomba, you have to jump on it. When there is a, so example, who taught it? Basically, when example instructions like, when there is a duck, you have to jump on it. If there is a star, you have to take it. If okay, to win. Okay, so who wrote that? Who wrote that aspects? Who taught? Okay, yeah. So exactly. So it was all a machine learning. Some of us got an impression that that developer who was showing that video, he actually wrote each and every aspect of winning the game, but it was all learnt by his program automatically. because in the same video he goes further and demonstrates the the same algorithm also played other games very well, other games which were completely unknown to it. Okay, so yeah, all right. Now, so in the last discussion we talked basics about machine learning. The live demo of that Mario game must have uh, thrilled some of us, and so those are the kind of jobs that you leave to machine learning. Okay, and in basic terms, the machine learning has various the three basic types. First is supervised, where we had the labeled learning data, and a classifier can predict output of our unseen inputs. Okay, for example, in our last Goomba example, it was a supervised learning. The developer told his program to look for a the developer told the program to look for a particular memory location for the results as well as the current state, as in it told the program that this is where the score is, and this is where the whole state of the uh, system is. So labeled learning data is what provided by us in the form of we basically told it to get the data from various locations, and and then we created a classifier, and it automatically started predicting output for unseen inputs. So that is supervised learning. Similarly, a supervised learning example would be that you have a spam filter. And a spam filter, basically, you have got, say, thousands of spams already. You have got thousands of emails which are marked as spam, and you know for sure that these are spam, and you want to train your spam filter on top of that. And once it is trained, then it will automatically start marking the new emails which you receive as spam. Okay, so that's the job of spam filter, and that's also again is a supervised learning. Now, what constitutes as unsupervised learning? Okay, so in unsupervised learning, we don't have trading data as such. We have certain data, and in unsupervised learning we just give it this data and tell it to find some pattern. One such pattern could be group this data into 5 buckets. Okay, just group this data into 5 buckets, and it has to automatically find the similarity index between the data. For example, given all the species and their properties, group them into hierarchies. Okay, it is an unsupervised learning task. Okay, we are given all the species, what do they eat, how many hands, how many legs they have, whether they live in water, whether they live, we have all of this data, what is their height, what is their body temperature, we have all of this data. Imagine we have all of this data, and we had to automatically form categories out of it, or maybe we have to form a sort of a tree that the humans and monkeys belong to the same parent, and that parent belongs to something else. So if we have to do this kind of a classification grouping, then unsupervised learning would be the way to go forward. The other example of unsupervised learning would be that automatically categorize my email into three buckets. Okay, automatically categorize my emails into three buckets. Now, how would it figure out that part? Is something very interesting. Okay, so Tarak's question is, so is it that particular keyword would be given a value as spam it is? Yes. So basically, when we are training for spam, we basically first manually mark things as spam. Okay, people would be marking the emails as spam, and then spam filter keeps on getting smarter day in day out, and then we keep on feeding that to our spam filter, and afterwards, after it gets trained, it starts serving really well. Correct. Emails just like social promotion and inbox in Gmail, that's unsupervised learning. Okay. So third is semi-supervised learning data. And this is semi-supervised learning is part of the data is available. For example, if we have to do the image detection automatically across the globe, right? We have to, given an image, we have to predict whether there is a what are the objects available in that image, right? Now in this case, in these cases, and you plan to use the data from across the globe, so what will you use? You will try to infer the input data from the file name. You might try to infer the input data surrounding the text, the text surrounding the image. Okay, so we will have only partial labeling information of the content, and that partial information may not be 100% correct. So the such kind of problems are called semi supervised learning. Alright, so there are many examples of machine learning, and this list is just a very small one. The fact that the face recognition algorithm as of today have become like 93% accurate. Alright, so machine learning is basically really improving fast, and it's able to deliver the results very nicely. As of today, the image recognition part or the voice recognition part has gone really well, such as automatically transcribing audio has become really well. Okay, so starting with the general recommendation ideas like recommending friends, recommending dates, products to the end user, classifying content into predefined groups. Okay, and this the other example you might think about in the in unsupervised learning is aggregating news together. If you use news.google.com, it aggregates the news from various sources automatically. Alright, so there are these many examples. You can go through the list. Okay, these, because these examples are just few of the. So is my voice not clear to other people? Is it breaking? Hello? Okay. So everybody is able to hear, so no, I don't have to worry. Awesome, awesome. So yep. Now, okay. So these are the few examples. All right. Okay. All right. So the machine learning tools, such as there are many machine learning tools, starting with the most primitive form of machine learning. Can somebody tell me what is the most primitive form of learning? Where given an input set of data, we predict the future data. Is the most primitive one is plotting a graph, correct? We are given 20 points on the graph with xy values, so we draw those points onto a graph, then we extrapolate the graph, and then we start predicting the future, meaning predicting the value of y based on x or values of x based on given y. All right, so that is called, so that is like most primitive form of prediction or machine learning. Okay, but the things have moved far beyond that. If your value, you have multiple variable like hundreds of variables and you have to do prediction, it's pretty difficult to do that. But thankfully these days most of these algorithms have gone really well and they are doing pretty good job. All right. So, is the voice breaking for everyone or is it only from Huda? Voice is not breaking. Okay, good. Alright, perfect. Perfect. So, these are minor teething issues for some of the candidates. Alright, so now we are talking about machine learning tools. So when we have a small data in like few lines, say 10, 15 lines, we could simply draw the chart on the whiteboard and start extrapolating the data. Alright? But the moment when the data grows from few lines to few KBs or maybe 1 MB, 2 MB, okay, then you start moving the data from your usual Excel sheet or to tools like MATLAB, Octave, R, okay, for processing. Yes, this session is getting recorded, Harshal. I'm using another tool today. I'm not using GoToMeeting, alright, for recording. I'm using something called Apple. You can see this dot here at the top. Okay. Okay. So in those cases, you might have to use MATLAB, Octave, or R. But the moment your data starts growing beyond MBs, then your analysis and visualization tool start to differ. For analysis, in case of say 2 GB, 3 GB, and from hundreds of MBs, you might like to use tools like NumPy, SciPy, Veka, and these kind of tools for analysis. And for visualization, you might like to use different set of tools. Now, the moment your data grows into terabytes, then your almost all the tools, including R, SciPy, NumPy, all of those tools are fairly useless because almost all of the other tools rely on the fact that they will be able to load the data into the memory and then churn it. Okay, but in case of MAHOUT and AMLib, these tools are able to do the processing onto multiple computers, loading parts of data onto different machines. Yes, last week's sessions are correct ones. Alright. Last week's session got recorded correctly. It's just the last to last week's sessions gave me a lot of troubles. Alright, Hura. Now, Okay, so that's where the MAHOUT comes into play. When you have to do classification or grouping or basically general training kind of work or machine learning kind of work on gigabytes to terabytes of data, then you use MAHOUT, Giraffe or AMLib. Okay, so a general way would be the things which we are going to discuss it. We are going to find out the recommendation. Given a huge data about who likes which movies, we are going to predict that who will like which movies. Okay, so given this kind of data, like this kind of data, there is a person, there is a movie, and the rating he has given. So Sandeep likes Matrix 9, 9 out of 10. Sandeep likes Casablanca 9 out of 10. Then there's Kumar who likes Matrix 9 out of 10. Then Kumar likes Shawshank Redemption 8.5. Now based on this very small data, we are going to do the recommendation using MAHOUT. And since MAHOUT is basically a collection of algorithm, we are going to use a particular algorithm for recommendation called similarity log likelihood. There are many such similar algorithms, and these algorithms, their performance does not vary too much. You just have to figure out into more details that which algorithm is better for you. All right, there's a cosine, there are other algorithms, so going into deep into those algorithms will be out of the scope of this session. So after this we'll get a recommendation that Kumar would like Casablanca as 9 because Kumar and Sandeep are 50% similar, okay, at least 30% similar, and because they have one common movie out of 3 total movies, right? So they are 30% similar, and therefore we start giving recommendation of the remaining movies to each other, and that's how it is. Okay, so most of the algorithms work on the principle of finding which users belong together and which users belong together, and therefore we will do the cross selling kind of thing. All right, the other use cases could be collaborative filtering, clustering, classification, and frequently item set mining. So in case of MAHOUT, these are the 4 general kind of problems that MAHOUT solves. One is recommendation. Collaborative filtering, it means recommendation. Clustering means grouping the elements together based on various features. And classification is basically given the past history that this thing is spam, this thing is a proper email, it starts classifying the elements. And then there is something called frequent item set mining. Given the history of people, it will automatically figure out that these 3 things belong together. Okay, that sounds like clustering, but it's little different. It basically, given few items, it will give a recommendation that if you people who bought these things also bought that one. So that's called frequent item set mining. Yes, we will cover MAHOUT on the top of Hadoop. That's right. No, we will not cover in frequent item set mining in detail, but this is standard algorithm provided in MAHOUT. You can start using it right away. And the best resource to use is, so okay, so use cases, first is collaborative filtering recommendation. For example, Amazon's recommendation that you may also like it. Okay, that is that, or people who like these movies also like that movie. That is recommendation. Clustering is these items belong together. Okay, given a lot of data, we don't have to tell that these users like this or that. Given the whole data, it will automatically cluster them together. We just have to tell how many clusters it has to form. Then there is classification. we have classification, and based on classification, in the classification we have the past training data, which has the information about lot of items in that what was classified as what, and based on this data we should be able to classify unknown items. And then is frequent item set mining. Basically, given a shopping cart, what else can you recommend to the user? Okay, so although that sounds like a recommendation, so does it cover random forest classification case? It does cover, I think, as far as I have gone through the list of algorithms in the library. It does cover uh, random forest, and even those algorithm where the elements are in the tree. You have to create the hierarchical clustering. Those kind of things are possible. All right. Now, yeah, dysentery. Yeah, those are the basic things. All right. So today, what we are going to do is, so this is one assignment which we could have given to people. Okay. Now let's just move on to next session. This assignment is no longer required. Alright, so we have already, so basically we are going to use the data from movie lens. Okay, the movie lens data basically contains the details about movies, and as we have shown you in earlier chapters that the movie lens information, we downloaded it and imported it into Hive, correct? So in the similar fashion, we could today also we could load the data. Yeah, I know Uzi is left. Okay. So since Uzi ties everything up, so it would be better that if we discuss the Uzi at the last point. Today we are going to discuss two important topics. One, I will quickly take you through MAHOUT, and then we will dive deep into Spark. Alright, we will go through various use cases of Spark. So stay tuned. So here what I'm trying to do is, right now I'm going to show you how to do the recommendation. First, let me get the sample data, and sample data I have already downloaded. This wget command -nc is basically to download the file. Okay, so let me SSH. You might want to putty, and I'm just loading that. Alright, so here we are, and we are going to basically go to my folder, and I have already this 1 million data. You see ML1 million. Alright, here you can see clearly that there is something called ratings. I'll show you what does ratings look like. Alright, so ratings contain, and to know more about this data, you can have a look at what does readme say. Okay, readme says, alright, here, so it basically readme tells you about what all is there in the input. Okay, so let me go through each file one by one. So movies.dat contains the movie ID, the name of the movie along with the year, you can see, and then genre of the movie. Okay, so these three parts of the information is provided to you in movies.dat. Alright, now we can say WC minus L, and you can see that there are around 4000 movies. Next is that tail minus f ratings dot dat. Okay, in this you can see that there is a movie, there is a user ID, there is a movie ID, and then there is a rating, and the last one is the timestamp. This information you can get it easily from the readme. Okay, now we have got second file containing who rated which movie how much. Third file we have is our users.dat, right? Users.dat. Okay, it has tailman's f is not required. It has the information about the users. So this particular user is male and age is 25, and then there is other information about this user. Okay, now we don't need any of this. All we need is this particular file. Okay, the ratings file. Okay, just based on this file we have to do the predictions. Okay, so again, what we are trying to do is we are trying to prepare the recommendation based on the past history of the user. So this is a huge file. You can see wc minus l and ratings.dat. Okay, it has got 1 million ratings. Okay, total 1 million ratings. Now to churn this kind of data and prepare recommendation is a huge task. It has to be done by multiple computers simultaneously. Alright, although if you have really huge memory, you can execute this on a single computer, but if the data grows to say 10 million, it becomes almost impossible to get it done using a single computer. Even if you are using really fast machines, if the data is beyond 100 million or beyond say 10 billion records, then it becomes almost impossible to use the local machines, one single machines. Now here in those cases MAHOUT works really well, because MAHOUT works on top of Hadoop in order to give you this data. So all MAHOUT needs is a nice file which is comma separated instead of double colon separated, and it needs only 3 files. You see these 3 files, and the ratings should be between 0 to 5. That's all MAHOUT wants. MAHOUT wants 3 columns instead of these 4 columns. It wants 3 columns, that too comma separated, not double colon separated. So our job first of all is to convert ratings.dat into CSV format. So what will you do in this case? Anybody? So we have to convert this into something which Hadoop MAHOUT understands. MAHOUT understands comma separate format, and MAHOUT demands that there should be only 3 columns. This we are doing only for the collaborative filtering part, or we call it recommendation. So anybody, how do I convert this data into comma separated format? Quickly. And we just keep only 3 columns rather than 4 columns. Yeah, so is the objective clear to everyone? Yes. How do we do that? Which tool should I use, Vikas? These are a million records. Okay, and which command do you think I should use, Nitika? Anybody else? All I want to do is basically replace double colon with comma, and do not ask me to load it in an editor, because loading into any of the editors will become almost impossible. Okay, and for substitute, so using grep we can only grep, we cannot substitute. Also, we will have to move this data to our HDFS. So why don't we start with, okay, so yes, alright. So you can see here what am I trying to do in the second command. I'm trying to use a command called awk. Awk basically parses this data and saves it into this file. Alright. So we are lucky that our data is small enough. Had our data been far bigger and already had been on HDFS, then we could not use tactics like this. Okay, we could not use tactics like this. In those cases, what will we do? If this data was in pig in HDFS, so we could have used pig or hive to convert our data from one form to another. All right. So I'm leaving that to you to use pig for this. Okay. So here is our command. Not this way. So now this has basically converted it into uh, this format. Or if you want to just test this command, what you could do is you could basically say tail, okay, and it would give you this. It all it does is it basically splits the field by colon and prints only first three fields. Okay, so now we have prepared our ratings.csv. Correct, you can see that, and we can go forward and use this for our MAHOUT. But before that, we have to copy this file. We have to copy this file to our HDFS. So we used Hadoop fs copy from local, and the file already exists. So let me just say -rm. Okay. So it is deleted, and we can see, okay, now we are copying ratings.csv which we just prepared onto our folder onto HDFS. Okay, so you could use multiple things here. Ideally you should be using pig. If you want, I can demonstrate to you how to use pig. Basically load this file, then load this file using a pig catalog with colon as the separator, and then store the data, then use the for each to pick only those fields which are relevant to us, and then store the resulting data set into HDFS. Alright. Note that the pig storage use only single character, so you will have to use single colon and skip the null columns. Okay, because double colon will become two columns actually. Okay, so you'll have to skip one column. After that, once we have copied it into Hadoop, what we need to do is time is now to launch MAHOUT. So before launching MAHOUT, let's set the Java home path, and then we start with launching this. Now, but before that, we'll have to delete our old folders, because okay, alright, now there will be some temp directories also. Okay, I need to clean that up. So there will be temp directories. Alright, so here alright, so anyway it will tell us what to delete. Okay, let's launch. So this is our MAHOUT command. What does it do? It says MAHOUT that we are looking for recommendation, item based recommendations using this particular strategy or algorithm called similarity like log likelihood, and then this is our input file, and this is going to be our output folder. Alright, and here we launch. It should generally give an error that temporary file already created and all. Yeah, just a second. The output directory called tmp already exists. Alright, now let's try to execute the command again. Now it will take a considerable amount of time. Okay, so we'll let it running and move on, and by the end of the session we'll get the results. Alright, it'll take around 30 minutes to run. Alright, so other than similarity log likelihood, okay, there are other algorithms also, and the kind of output we will get is this. We'll get this user might like this movie this much. Okay, this user might also like this movie this much, and so on. Okay, it will store in the records folder, and records folder will contain parts. Alright, so it has started working, and it will, once it is done, it will finish it. Okay, so this is what is going to be our output, and once you have done this, you can join with other tables and push it to your web server using Scoop, and from the web server you can start serving to the end users. Okay, because these recommendations are going to be in KBs, not in GBs, so it's okay to take this data from here to your web server in your database and then start serving to the end user from there. Alright, we start showing to the end user from here. So that is the role of MAHOUT. So this simple command, basically given an input file having 3 columns, item, product and rating, it was able to give us how much each user is going to like a particular movie. Alright, so basically here we talked about only movies. Here these 3 columns could be any product, any user, any product and the rating, just that the rating has to be something between 0 to 5. Okay, the other algorithms are similarity log likelihood, similarity co-occurrence and Tanimoto coefficient. and there are these algorithms to compute the distance or to compute the similarity index between various users and to prepare the recommendation at the end of it. Okay, these algorithms do not vary too much from each other, and generally you can basically use the Nimoto coefficient, cosine, Pearson correlation, and log likelihood interchangeably. Okay, their accuracy is hardly few percent. The accuracy of these algorithms hardly differ by few percent from each other. Yes, these are inbuilt algorithms. These are the libraries provided by MAHOUT to you. Okay, and MAHOUT has written everything in MapReduce, and it's essentially executing things in MapReduce right now. All right. So all the basic mathematical operations have been converted. Say for example, matrix multiplication. All of these algorithms are converted into MapReduce. Yeah. Here we are just trying to use it, and if we know how to use this these syntax, then we can go ahead. All right. So what do you want me to explain, Nitika? Okay, so we just have to use these algorithms right now. Getting into MAHOUT and going to more details into MLlib, other details will be far beyond the scope of the session. All right. So these are again the same slide. Now, so it will not be possible. It will be beyond this scope of this session to go into the MAHOUT beyond that point. Okay. So the idea was to demonstrate to you the very introductory command in MAHOUT. I would strongly recommend, if you are inclined towards going into, okay, okay, so go ahead with the MAHOUT page. Okay. Okay, go ahead with the documentation. They have a very decent examples, and you can start from there. All right. So now I'll move on to Spark. All right. So while our MAHOUT is running parallelly, you can see that it's executing MapReduces. So today we are going to discuss Apache Spark. Apache Spark has been, in the recent times, has been really fast as compared to MapReduce and other systems. It's a fast general engine for large scale data processing. And okay, so Apache Spark is really fast MapReduce, and it's 100 times faster than the Hadoop's traditional MapReduce because it utilizes memory really well, and even on the disk it is around 10 times faster, which they claim. Yeah, it builds on the similar paradigm as MapReduce and is integrated with MapReduce. Okay, the only downside of, although the Spark sounds great and everything, but there are few downsides of using Spark. One is it consumes the memory, does not leave the space for other processes running parallelly. So if you have multiple processes running on your cluster, then some processes might starve. Okay, and I mean, it's a little greedy in that nature. And if one person basically there are to program in Spark sounds really easy, but it's very easy to make mistake also. Okay, in case of MapReduce, most of the complexity of memory handling was done by MapReduce for you. All you cared about how to convert my program into key value pair. Rest of how much memory to use, everything was taken care by MapReduce. Okay, so it's easy to screw up. It is easy to hurt others while you're using Spark on the cluster, but it's really fast, and it's basically quite getting mature and getting adopted. All right. So similar to MapReduce, the way we have on MapReduce, we have MAHOUT. MAHOUT was running on top of Hadoop MapReduce earlier. Now they are also migrating to Spark as of today. So similar to MAHOUT, we have here MLlib running on top of Spark, while Spark runs on scheduler such as Yarn. Yarn on top of Yarn we were running MapReduce, right? So MapReduce and Spark are competitors. Hadoop and Spark are not competitors. Okay, MapReduce and Spark are competitors. Okay, but if you are comfortable with churning petabytes of data at, say, in few hours, then Hadoop is a better solution. If you want to handle gigabytes of data in fraction of seconds, then Spark will be a better idea. Okay, so for faster processing you use Spark. For more reliable and bigger processing you use traditional Hadoop MapReduce. Okay, so both look like a competitor, but they are not going to replace each other very soon. So Spark relies on Yarn, or if you have Hadoop cluster already, if you are dealing with big data, chances are you already have Hadoop cluster, you can install Spark on top of Yarn. Okay, the way we have done, we have just told Spark that this is where our Yarn cluster is. Rest, it communicates with Yarn and get itself executed over the cluster. Okay, we did not have to install Spark on all nodes in our cluster. Okay, so Spark runs either on Yarn or something called Mesos or something like standalone scheduler. Standalone scheduler is not something recommended because it's only for testing and for single node. And on top of Spark, we have Shark, which is similar to Hive. And on top of Spark, we have Spark Streaming. Spark Streaming just one use case of Spark in case of handling the data in real life. And we will also go touch a little bit on Spark Streaming today. Then we have, similar to Giraffe, we had Giraffe in Hadoop MapReduce, which was the graph databases for computing the complex graph problems such as PageRank or network of friends. We have here GraphX, okay, similar to Giraffe. So basically, Spark itself is being developed every day, and lots of libraries are being ported onto Spark. Spark runs any logic you give it to the multiple computers, and that is the strength of it as compared to other systems like R or other systems like SciPy or NumPy. Most of those systems do not work parallelly on multiple computers, therefore their strength is limited. While Spark gives you really fast processing on top of multiple computers, and therefore most of the libraries are being ported onto Spark. And when we say libraries are being ported, that means even the basic mathematical functions such as matrix multiplication, inverse of a matrix, or finding the solution of linear algebra, all of those problems are being ported, those basic algorithms are being converted into MapReduce and distributed computing. So that's the ecosystem. If you want to install on your own cluster, you can use this step. We have found out that since we are using CentOS and we are using Hortonworks, so they give us specifically built library. They means the Spark guys have given a specifically built library for Hortonworks and for CentOS 64-bit. So we downloaded that one. After that we unzipped it and put it in a folder. and we for the simplicity's sake we moved it into user lib so that it's accessible to everybody, and then we gave it a nice name by linking it in the last step. You can see that here we gave it a nice name, but link minus s means linking it symbolically. Then because we have given it a nice place, it's now located in slash user slash lib slash spark slash bin PySpark. So bin contains multiple binaries. So by default it gives you the Scala library one, meaning okay, let me take a step back. The way we will be seeing Spark would be like a command prompt from where we will be executing code, and that code can be in Python, Scala, or Java. But right now we are going to use PySpark, which is nothing but uh, Python plus Spark command line. Alright. Once we see it, then so if you are already on our cluster, then you can directly use our this URL. Alright. You don't have to install anything. Alright. So let me just check how are we doing with respect to, okay, so our MAHOUT is finished. Those who are inclined, they can check asgiri/racos and you will get the result. Okay, you can check using racos, asgiri/racos. Okay, it has taken around 11 minutes. And what is going on? Alright, so you can see that this is the file that contains our data. Okay, so we can see alright, so you can see this here. It has generated all the recommendations and we have the results. Okay, so if you want, you can go into more details, and right now it gives around 20 recommendations. Okay, top 20 recommendations, and you can configure that part. Anyway, going back to our Spark discussion, let's just show you first how to launch it. So do you guys want to take a break before we move forward? Alright, so this is the command prompt of basically Python. So if you guys have used Python, it gives you a nice interface. So I'll show you how does a Python interface looks like. Python interface is this. Okay, here you can start writing your program in Python. Okay, so x equals to 1, we said. If we say x plus equals 1, it will increase x by 1. If we define function called ff, which basically does nothing but returns the square of x. Okay, so if we say 2, then it will give us 4. It will give, so this is the most simple form of programming. Okay, so we can basically, as we are writing the functions, it is executing them line by line. So this is our normal Python program. Okay, okay, so should we take a break, guys? Alright, let's take a break for 5 minutes quick and then come back. Alright, okay, echo break for 5 minutes. Back by 9:39 p.m. IST. So Tarak's question is that he has missed 3 to 4 classes. So in the morning one, in the morning session, we are discussing right now. We are discussing Hive actually. Okay, and tomorrow would be probably HBase. So if you want to join there, you can join there for those classes. Okay, you get in touch with me, and yeah. Alright, so we were talking about the Python command prompt. Okay, Python command prompt is very simple. All you do is when you have to write program in Python, you can basically start doing it. And once you have tested everything, you can copy paste your commands into a file that becomes your Python script. Okay, so you can write for loops, whatever you want to write. The more important part here is I wanted to show you the way we write a function. We defined a function, we executed the function, and we can keep on executing it as much as you want. Alright, so that's a Python function, and general syntax of programming would remain the same the way we have studied. Alright, there's no complex classes right now. We are not talking about classes, just basic things. So variable declarations, for loops, those are the kind of things we'll be using here. Alright, now let's go back and to our Spark. So this is Spark. Spark is nothing but you can see that it's similar to Python. Okay, it's a command prompt, same as Python, just that we have an additional Spark context available as SC. So all the commands which we just showed you will work fine the way we have defined earlier. Okay, so the way we defined function earlier will work just like fine, and we could say exact same way. So you can see that. So everything is just normal except for we have got extra object called SC. SC is the handle into Spark. Okay, SC is the entry point for Spark. It's like providing additional library in Python. Alright, now let's go ahead and so that was launching of the command prompt. We will go into more and more details as we go ahead. So first and foremost, the interesting concept which we need to understand is a concept called resilience distributed dataset. Okay, so whatever data we want to churn in Spark, we have to prepare that data set. Okay, the way in case of pig we loaded that data into a variable, similarly in Spark also we will load the data into a variable. That variable will be called resilience distributed dataset. And why do we call that? Because that kind of a dataset is essentially spread across multiple machines, and in case any of the machine goes down, it automatically rebalances it. Okay, so resilience dataset you can think of as if here it's running on 4 nodes, 1 2 3 4, and you can think of resilience dataset as huge array of values. Some of the values are on one machine, some of the values are on second machine, and some are on third, and some are on fourth. Okay, so we load the data into RDD. We can load the data into RDD from any of the sources, but our preferred source would be HDFS, because there it does all the cleverness such that it utilizes the node for RDD which are closer to our HDFS. So it does all that cleverness. But if you are loading the data from external sources, there will be transport of the data. Alright, now the RDD, as we say, can be kept in the memory as well as can be spilled over to the disk. Okay, and RDD is can recover from node failure. Okay, so there are, and this RDD in general is generally a simple array, but you can keep key value pair also in an RDD. Okay, a collection of key value pair. So it can be either a map or it can be an array. All right, in some cases. Now, on an RDD, on a resilience data set, what we do is we do operations. There are two kinds of operations we do. One is transformation, other is action. In case of transformation, that code will be running on each node, and in case of action, the data will be brought back to the back to you, basically. Okay, back to the place where we launched everything. Okay, so there are these two kinds of actions which will be running through. Okay, and I'll show you what a kind of transformation and action, and that should basically give you a very good idea about what is Spark. Okay, so Spark is essentially the most important concept in Spark is resilient dataset, which basically an in-memory representation of the data, and this in-memory representation is such that if you have 5 computers each having 10 GB RAM, so it will basically consume around 50 GB RAM. Okay, so a resilience dataset could be as big as 50 GB, but if you make the resilience dataset such that it is also spilled over, meaning part of it is also on the disk, then you can handle any kind of data. Alright, so let's do first thing first. You remember our big.txt? That big.txt from HDFS we will load into a resilience dataset called lines using this syntax. We are saying lines equals sc.text file, and then we provide this. Okay, so we are on Spark prompt and we are saying, so it has loaded the data immediately. Okay, it has mapped it, and we have this lines dataset. Okay, we can also say lines dot length. What is length? Okay, so I think its size we'll show you. Lines.count. Yeah, so lines.count is actually sending the request to all the nodes and trying to get the data. Okay, it says that job aborted because of some reasons and the nodes have crashed. Okay, let me try doing it again. Alright, looks like the machines are full. Alright, let me try to launch it again. Wow. So let me try to see if our cluster is running fine. Yeah, cluster is down. Actually there is some process which is eating up everything. Okay, so I can see that. Alright, so yeah, so I'm going to basically ruthlessly kill everybody's process who is running on this machine. Okay, now we have this one. What is it doing? It's basically running somebody's jar. Okay, and there is another process that's running here, and then there is another process. So I'm just going to kill all of them. Kill -9. Oh, I think I'm making a mistake. PS tree. Okay, so we have so many things running, and there are some processes which are basically eating up everything. I'm sorry if it is your process, but it has to go. Alright. So this is my process only. Okay. Okay. Never mind. So let me see if something is freed up. Alright, yeah. So now you can understand that the memory requirements from Spark, that in case the memory is not available, it could not wait and it gave us the error upfront. Alright, it gave us the error upfront. So if you are observing keenly, then you will understand that in case just now we ran our MAHOUT, right? That did not bother us. It basically executed it even if there was very low memory. Why? Because it could it did not require too much of memory. Alright, so now we are able to execute our count function since we have freed up some memory. Alright, so now probably this exercise was good. It gave you the exact reason why, because it's a very difficult thing to explain to lots of people, that what is the downside of using Spark. Okay, because if there is some process running at the time, so it's not really tolerant to the memory issues. It's tolerant to other issues. Okay, so are you guys with me? So we were able to load our lines RDD, and we were also able to find total number of lines very quickly. Okay, by default, when we say load it as a text file, it essentially converts each line into an element in the RDD. You can think of now lines is nothing but a big array of line objects, and each object is a line. Okay, alright, so great. Now since we have loaded the data as lines, now first thing would be to break each line into word and then count it. Okay, that we'll do it later, but let's do some other exercises first. Imagine that we want to count the total number of characters in each line. Okay, now for that we'll have to do transformation. And what exactly is transformation? A transformation is a function which is run on each node parallelly on the whole cluster. Okay, whatever transformation function you provide, it will run on the whole cluster parallelly. It will generate another data set on the Spark cluster. It will not give you the result back. And what does it mean by giving the result back? The way we just executed lines.count, it gave us the result back. It brought a value back to the user, correct? Gathering the whole information from all the nodes. So that is not the transformation. Count is not the transformation. Count is an action. While a transformation is something that happens on all the nodes parallelly. Also, a transformation gets executed only when some action happens. When we say transform this to that, Spark takes a note of it, and the moment when we say run the action, then it executes things. Transformation is transforming the data from one form to another, just like in pig script. In pig script, we took a data set, we applied filter on it, it generated another data set. Similarly, here also, the transformation is that way. Now, this diagram does a proper depiction of transformation. Here we are showing that we are loading data from this HDFS file system into RDD, and then we are applying transformations, and again we are generating another RDD back into the memory. Okay, and there is something called a driver application. Right now we are in the driver seat. We are the driver application because we are executing everything from the command line. So anybody who launches the whole process is the driver application. So there is a driver application, there is a Spark backend which is running, and we are contacting the Spark backend for doing for creating an RDD, and then creating a transformation on top of it. Alright, so an example of RDD is map. Here the definition of map is, map will take an input value and give an output value. Okay, it's as simple as that. Map takes an input value and converts it into output value, meaning given an RDD is nothing but an array of values. Given an RDD, it will convert an RDD into another RDD, the map function, and how it converts is up to us. Okay, so for example, right now our RDD is a big array of lines, right? Each element is a line. Now let's say we want to convert it into array of line lengths. Okay, array of line length. So first we have to define a function which basically computes the line length. Let's say first let's define a function, define line length function, and what does it do? Whatever string we give it, it will return the length of that string. Okay, let's test our function, line length and Sandeep. Okay, so it gave us 7. So it means the code is working fine. Now we want to run this line length on each of the element of our lines. Now this lines is an RDD. It shows you clearly that lines is an RDD, meaning it's a distributed data set. Lines is, some part of the lines are on one node, some elements of lines is on another node, some element of lines are on another node. Okay, and to just peek into it, we can say take 10. Okay, and it will just get you 10 records out of it. You can see these are the 10 records out of the lines. Okay, this is comma separated. U means it's a Unicode. That's the way Python represents a string. This is one line, this is another line. So this is your resultant data set. So this is our resultant data set. So lines contain, this lines data set contains array of lines. Okay, now what we want to do is we want to run a function via a transformation called map, and that function is ll, right? What we want to do is we want to convert this array into the line lengths. So what we do is we say lines dot map, and we provide our function called ll. Okay, so we have to say llrdd equals lines dot this. Now llrdd, if you say take 10, you will see that it has done a good job. You can see that it has basically, if you let me, yeah, sorry, so lines dot take 10. Now so let me just copy paste so that you can get the feel of. So these are the first 10 lines out of it. Okay, these are the first 10 lines, and when the length of this is how much? This. Okay, now you can see here. So the length of from here till here is 65. You can see at the bottom. Okay, here at the bottom you can see this is 69, meaning from here to here. Then here to here there is a length, and here there is line length 0. So you can see the line length equals 0. So that way. Alright, so there is 1, 2, 3. Okay, So now you can see that we have computed the line length of the RDD. Okay, so LLRDD is another array which was generated due to transformation. What we did was we had one form here. Okay, we had one resilience data set here. Transformation converted that into another data set. All right, and that data set contained now the lines. Okay, so that is one form of transformation called map. Map basically takes a function. In our example, it took LL and basically gave to LL each element of the RDD, and whatever was the result is it is stored that result into another RDD. Okay, so it returns a new distributed dataset formed by passing each element of the source through a function. Okay, function called func. All right, so now you can think of map as if it's like your for each statement of big. It went through one element at a time and then generated the output. Okay, so map function here is little different from what we have seen in past. Here it's one element at a time. It takes one element and it is mandatorily supposed to give an output. Okay, so if our, let's assume that, okay, so let's see how many records were there. If you guys remember, when we said ll.count, total number of records were these many, right? These many lines are there in our input. Now in this one, how many records would be there? Can anybody tell? In LLRDD, if we say count, how many records are going to be there? Quickly. Yes? So this array, so there was a lines array. Total number of lines were 1,28,000. Then there is another array which we just produced after running map on top of this lines array, and the total. So yeah, okay. After we have run a map function over each of the element producing the line length, right? How many elements would be there in this? If the total number of element in this were 1,28,000, anybody? Okay, I think nobody got it, so let me explain it again. So we are transforming a data set. That data set is what? The lines of our big.txt. This data set is nothing but an array of lines. Okay, is everybody with me? Abhishek is with me. Who else? Okay, Huda is with me, and are you guys listening or you have gone to sleep? Alright, so let me try to explain again. So what are the things we are trying to do? First, as a first step, we loaded our big file as an RDD. What does it mean? It means that this RDD is a big array of values. Array is what? Array is a list of values. We loaded that into an RDD. Okay, now we are trying to do a transformation on top of that RDD, and what we are trying to do is we are trying to compute the length of each line. Correct? Now for that we are using a transformation. There are multiple kinds of transformation. The most common, these are the most common ones. So we are using map function. What does map do? It as an argument, it accepts a function, and this map function is part of the RDD, meaning it takes the function from you, it runs this function on each element of the array, and whatever is the resultant, it stores in another array. Okay, if the original array had 1 million lines, how many lines, sorry, if the original RDD had 1 million elements, what will be the result, how many elements would be there in the resulting result of map? Okay, so what we did, let me again show it this way. So we have got lines equals to, you can see that lines equal to this, we loaded the data, and all right, is my voice clear? So we loaded the data into lines, then what we did was, this is our lines, what we did was, on lines we said, in the meantime we Hi. So yeah, my connection is breaking badly. So let me set up things in between. Okay, so let me try to set up an alternative connection in meantime. Alright, so yeah, extremely sorry for that. Alright, so here we are. Now what we did was, we loaded this data into this data set called lines. Now we have defined a function called ll, and what it does is, it computes the length of whatever you give to it as argument. Okay, so it basically does find the length and return the length of each array, each string which is passed to it. Okay, so you can see this. Alright, now what we are trying to do is, we are running map. Map means, you here in the context of Spark, what does map means? When we say map, we pass the argument as the function name. We tell that here is my function that to be used for the map. Okay, so whatever you have here, okay, will be applied a function, and the resultant will be stored on this. Okay, is it okay, or should I take another example? For example, let's take another case. Okay, there is another variable called values, and we are trying to create it from a normal array rather than our. Okay, so you can see this, that there is this array. To convert this into RDD, we have to say sc.parallelize. Okay, if you have to convert a normal array into an RDD, you can use sc.parallelize. Okay, now you can see this. Did I make a mistake here? PA parallelize. Okay, yeah. So values is here. Now if we want to say, do the cube of each element, so we can define our own function called cube, and whatever value we are giving, we will return x into x into x. Okay, and then we will say cubes equals values dot map, and then we can say x, not x but cb. Okay, now what will happen is, what will cubes contain? Anybody? Okay, let's call it, what will c contain? Yeah, here you can see, right? Now, okay, so yes, it will contain the cubes of each value. Yes, I'll show you that. So we have values right now. We say, how do you say, take all or collect. I think collect is the, collect basically brings it back from RDD to normal array, right? So it, you can see that our values contain this. Now next thing what you can do is, on the values we define a function called this one, which basically each value is going to be multiplied by itself thrice, and you can test what is the value of 1. 10 is 1000, 11 you can see. Alright, next is we are going to apply this function called cb on each element of the array called values, and the resultant will be stored in c. Let's see what is there in the c. Okay, now you can see that it's basically the, our function has been applied on each element, and the resultant has been stored into the new element, new values. Okay, so is it clear to everyone? The data type of c is automatically set. Now question to you is, here in this syntax, question is based on this particular one. If length of values is 2000, what will be length of, or the count of values is 2000, what will be the count of c? Meaning, if values contain 2000 elements, how many elements will c contain? Correct? So it's basically a one-to-one mapping. Great. It's basically a one-to-one mapping. That is the difference between our map. Great. This is the difference between our normal map and our Hadoop MapReduce. In case of Hadoop MapReduce, we took an input value, we gave out key value pairs. Here, we took an input value, we returned a value, and it was mandatory to return a value here. If we did not return, it will assume it to be null, but still there will be something. Alright? So basically, this is a transformation. This is a transformation where one data set is being transformed into another data set. There are other kind of transformations other than map, called filter. Now, okay, Tarak's question is, can we have both values of x and x cube together instead of 1? Yeah, so in those cases what you will have to do is, you will have to return things like this. Okay, it will become a tuple. I'll show you this. Okay, so you'll have to define functions like this, which means it automatically becomes like a object and will be stored there. So you can see that. Okay, now you can see that. Is this what you wanted, Tarak? Alright, so you can do those kind of things, but still, if you count the length of this array, it basically is the length is same. It's just that each object is a tuple. A tuple as in each element contains two values. All right. So that was map. Now there are other kind of transformations, and those are really interesting transformations. Other is filter. So we have huge data set. Out of this, we only want few data sets, few values. For example, in this one, we only want the elements whose first value is even. Okay, we only want all those ones. So what we do is, okay, or let me try to do things in a simple fashion. Let me go back to what we were doing, and here we go. We created this, and then we said c equals, okay, and c dot collect. Collect is just for our satisfaction, as in we are trying to bring the data back, and collect is called an action because it's executing things. Now out of this, we only want even elements, those elements whose values are even. Okay, out of C we want only even, so we say only even is a name of the data set we are saying, and we say values dot filter, and we will provide our filter function here. Let me first write the filter function. What would our filter function look like? Our filter function would look like def, okay, and only even, okay, and whatever value you give here, it'll say if x divided by 2 equals 0, then return true, okay, and else return false. Okay, now good part here is that it's quick to test, so we can quickly test only, sorry, there is a mistake here. It doesn't matter though, it's just our name. Whatever we want to keep, we can keep. So we can see that we just created a function called only even, and we can say 4, it returns true. We say 41, it returns false. Correct? Now we have defined a function called only even. This is the filter function which we have to supply to a transformation called filter. Alright? Now you can see that only even contains only even dot collect. Let's gather all the values. So you can see that it's only 2, 4, 68 which is even. Out of these numbers, it's only 2, sorry, we have applied on the main one, that is values. We can also apply it on the resulting value. In those cases, if we say only even, then only 8, 64 and this number is even. So is everybody with me in this? So we filtered the total record set. First we applied a map, then we filtered. Then there are other kind of transformation functions such as flat map. Flat map is similar to map, but each input element can give out one or more output items. Okay, sounds good. And then we have group by key here also. So the grouping itself is a part of transformation. Alright, you can have a look at more transformations there. On this URL. So these are the kind of transformations which are available to you. And the way we had map reduce phases, here we have transformation and action. We break down our whole logic into transformation and action. Okay, but here the taking this call whether to create do something in transformation action is very obvious, because whenever you have to bring the data back from all nodes to local nodes, or in other words, if you have to convert the RDD back to a normal value, then that is called an action. The way when we said element.collect, that was an action. It brought the data back to our local machine from the whole cluster. Okay. Now there is something called actions. As we have been talking about, an action is nothing but it brings data from all the nodes to a single node. Okay, and there are multiple kinds of actions. One of the most popular one is reduce. It's basically action called reduce. The definition of reduce is very close like our, yeah, that's correct, Nitika, thank you. Count is also one of the actions, yes, and take n was also one of the actions. Now other three we have already used: take n number of elements, collect all the elements, or just count the number of elements. Now the one which we have not shown you and little more involved is reduce. A reduce is nothing but it will take your function and will apply to the elements of the whole list and convert it into a single value. Just like your combiner. If you remember our combiner, in combiner there were multiple values and it used to convert it into a singular value. And exactly like combiner, its behavior is cumulative and associative, meaning reduce function will be applied on the values again and again, because reduce takes only two arguments at a time. Any function which you want to use a reduce has to take only two values at a time. Okay, let me show you this. So let's go back to our main example. So this is what we have. Okay, values equal to this one, and imagine that we had to compute the summation of all the values. Okay, if we had to compute the summation of all the values, what is it that we will have to do? Okay, so first we have to write a function called summation. We define a function called summation and we say x and y. Notice that there are only two arguments in summation, because only those functions are valid reduce functions which take two argument and return a single value. Okay, so now we say total equals values dot reduce and we pass our function. Okay, what will it do? It will convert the whole array into a single value. Will convert the whole array into single value. So we define this. We can check this out quickly. Okay, so this is functioning very well. We gave two arguments, it converted them into summation. Then let's try to do this. Okay, alright, looks like again we are running out of memory. Alright, let me see what is the total containing. Now you can see the total contains 89, right, which is the summation of all these values. Alright, now our function was only taking two values at a time. How did it convert the full array into a single value? It basically applied your function again and again to reach to a single value. Okay, just like combiner. So it first applied on 1 and 2, then and 4 and 5 and 6 and 9, and whatever came out of it, it then again, so the way it must have done is, okay, so if you have this array, it got converted first into 3 comma 9 comma 68 plus 9 is 77, and then again it applies on two values at a time, 12 and 77, and then it summed it up. Okay, 89. So it applied our sum function again and again till we reach to a value. Okay, now you might say that this is great, and do you think that all functions are valid reducers? Can we use any function? Say for example, I'm typing a function just now, we call it AV, it takes two values and returns x plus y divided by 2.0. Okay, so what does it do? It finds the average value of two values. Will it compute the average value of our array? If we say our v equals or let's say avg equals values dot reduce, and we pass here, so now you can see that we are passing a function here. We are saying that this is our reduce function. So will avg contain the average value? Anyone? Nitika says yes. Who else? Yeah. So we wrote a function called AV, and the way it is basically reducing two values into one is summing them up, dividing by 2, and then it's doing it again and again. The way we did summation, it is going to do it again and again. So let's try to do it in here. So average value of 1 and 2 will be, anybody? What will be the first value here quickly? 1.5, correct? Now 4 and 5, 4.5, correct? 68 and 9, 33.5, that's correct, 33.5, yeah. And now average value of this and this, three, and average value of this and this, okay. Sorry, this will be as such because the first value has been consumed here. These two has been consumed. Now the overall will be 36.5 divided by 2, and how much is that? 18.25, correct? While the average value of this is, anybody? What is the average value here? So are we running in a sheer luck? 1 plus 2 plus 4 plus 5 plus 68 plus 9 divided by 6, which is 14.5. So if you compute the average in a normal fashion, the average is coming out to be this much. While if we are doing a reducer, it's giving us the wrong result, correct? Therefore average is not the right function, and you cannot compute the average that way. All right. You cannot compute the average that way. So what you generally need to do in such cases, for either you divide all the values by the total by running a map function, you divide the all the values by total count, and then you do the summation. Okay, because if you try to sum it up, it might overflow the integer, and therefore the summation and then division by the total may not be a great idea. All right. So similar to combiner, not all functions are candidate. Okay. So Tarak's point is, what does it mean by overflow integer? What I meant was the other strategy would be to first compute the summation and then divide by total, right? But in some cases, what would happen is, if the total of all these values is too big, okay, then the summation will overflow the integer. A better idea in those cases is divide each element by the total size of the array, and then sum them up. That will be better. Okay, so instead of summing them up, what we do is we sum up 1 by 6 plus 2 by 6 plus 4 by 6 plus 5 by 6 plus 68 by 6 and 9 by 6, and that will give us the average, right? So using one map, will be basically dividing everything by 9. We'll define a transformation called map, which will divide every element by 9, and then we'll define a reduce function which will basically sum up the things, and that's all. Alright. So just like combiner, we cannot, and notice that the summation values, even the binary search of Java was found buggy because of this overflow in 2012. Okay, and that led to a lot of problems. So every year I mean, these kind of things you need to take care of when we are dealing with big data. You have to think in terms of really big data. Okay, you have to be even skeptic about summation of values. And if you are doing product over here, then you forget about it. You can basically, you have to think about some other strategies. All right. Now next one is going back to the what we were discussing. Alright, so this is the reduce function. It takes a function and keeps on applying that function until it reaches to a single value. Let's try to demonstrate the result of our average function. That will basically make a little sense. So we have average, we give 3 comma 4, it gives us 3.5 if we give. Alright, now next is we say reduce, and here we go. Alright, and if we say average, it has 12.75, it's not even 18.25. Alright, so its strategy is doing it from the right hand side rather than left hand side. Okay, so if you start with the right hand side, then it will be different value altogether. So here it will be, how much, can somebody tell me? What is the average of these two values? It is for 38, 19, and then 1.5, and the average of these two is 19, 12, so it will be 20.5, which is 10.25. Yeah, I don't know, it might be doing in certain order, which I don't really know. Okay, so basically average function is not suitable for being a valid reducer. Okay, So you have to always take that into account, because what it is going to do is, the way it is going to work is, first it will start reducing on all machines. On each machine it will start reducing here, then here parallelly. All of these machines are converting their section of the array into a single value, and again these four values are going to get converted into single value by recursively applying the same function. That's how the reduce works. Okay, now question from Tarak is, can we use average of x comma y, return x by 2 comma y by 2? Yeah, no, that will also not work. Reason being, we are dividing by 2, not 6. Okay, all right, and therefore it's important to understand that reduce function can only be applied if, I mean, the way we have thought about the translation happening, if your reduce function is qualifying there, meaning even if you keep on applying the function again and again, still the results are okay. Like like for example, min, do you think is a valid reduce function? Minimum of two values. So if you have this, what will be the minimum value of this? 1, right? So no matter how you apply min, Abhishek, no matter how you apply min, it is always going to give you same result. Alright, so min of 1 comma 2 is going to be 1, 1 comma 4 is going to be 1, 1 comma 5, and so on. You'll always get 1 as the result. Same is the case with max, same is the case with count, summation, and same is the case with others. Correct. The max will also work well. Alright, can somebody give a function which is a complex one? Median, do you think median is a good one? Median will not be a valid function, because the way we'll be implementing median for two values will be average of the two values, and again we'll be trying to compute the average value, and that is not possible. Okay, so median will not be a valid function. Correct. Alright, now the same thing I have depicted here also, the way the functioning has happened. Now Spark provides you the shared memory kind of options. Alright, it provided us transformations where the one data set got translated another. It provided us the loading the actions, which basically started the whole process. Also it brought the values from all the nodes back to the end user. Okay, an action can also be saving the data into a file. Alright, now next is Spark provides us the shared memory, because when you have multiple processes running across the cluster, you lot of time you have to talk to each other. Okay, you have to inform each other. In case of Hadoop, that was very difficult. We always have to launch our own things, or maybe we would use Zookeeper for coordination between various map reducers. Correct. Now in the here, in case of Spark, Spark comes with something called a broadcast variable. All right. Can you hear me? Can you hear me? It shows me that the data had been disconnected for me. Hello? I think it's bothering us a lot. So alright. So for a moment I'm going to try out my other connection. Alright? I don't want this disturbance. Okay, so I hope you are able to hear me. Hello? I think it's very slow. Alright. Okay, so I think now it has been restored. I hope it will work fine. Alright, it is very irritating. Alright. Okay, okay. Are you able to hear me? So I'm having again the kind of problems on all the three connections actually. Looks like they come from the same source. Alright. So shared memory is like a broadcast variable. When you start your process, you basically create a broadcast variable, and whosoever is using this broadcast variable across the multiple node, they will be able to communicate with each other. The way they communicate with each other is by getting and setting value in the broadcast. Okay? The way so for example, when you start the process, you create a broadcast variable, and then you pass that broadcast variable into your map, or any transformation, or the reducer. Okay, transformation or the action. Alright, so in the similar fashion, it also provides you a way to gather the data from all the nodes parallelly, continuously, as in when the data is, everybody is printing out things, it's gathering it. Okay, that is accumulators are one way, and those situations where it does not matter in what order we receive the value, the resultant is going to be correct. Accumulators are good. For example, if we are counting number of lines from all the Spark applications, then basically accumulator will be fine. Okay, because it's just one way. all the nodes will keep on writing to the accumulator, and accumulator provides you the function like add, and that add is essentially that add means they will keep on pushing the data continuously to a one file. So accumulators are great for gathering the statistics from all the nodes in the real time. So for example, when we were counting our lines, or when we were doing say word count example, we could actually see the progress. We could see that how many lines have been processed so far if we could have used accumulator. Alright, so that's an accumulator. No matter in what order the values come in, if the results are same, if you are okay with the results, then it's you can use the accumulator. Alright, so here is an example of our MapReduce. So here is an example. We loaded the lines. Okay, we loaded the lines. Here we are loading the lines. Let me parallelly do it. Okay, we loaded the lines, fine. Next is we defined a function called lines to words. Okay, let's write this function and also test it parallelly. Line to words, and when we say Sandeep Giri is teaching, okay, so it basically converted it into an array of words. Okay, so now what we are going to do is we are going to utilize a transformation called flat map. Flat map is basically returning multiple values for each line. Okay, it's converting one element into multiple elements. Okay, so we are going to convert each line into a single word by using flat map. So we got words array. You can peek into what's there into words by saying take 10. Okay, just to see what's there in the words as of today. So right now this is an array. Okay, this is a RDD. Elements are one word, second word, third word, and fourth word. You can see that. Next is we convert this each word into key value pair. Okay, how do we do that? We defined a function called 2kv. So whatever we pass here to this one, say we pass, say let's say spark. Okay, and it will convert it into a pair of this thing. Okay, it's like a tuple as in pair of words. Okay, key value pair you can say, and the second value is just 1. Okay, it's just 1. So now we again executed a map function converting all the values into this format. Now let's see what is there into kv. Okay, you can say take 10. Now you can see that the has been converted into the 1, project 1, Gutenberg 1. Alright, next is we do the rewrite something called summation. Okay, good. Now there is an idea called reduce by key. Reduce by key is like group by with aggregation done by the function. Okay, this is our aggregation function here. So we say words, sorry, yeah, that's correct. Now let's have a look at what it is here. Alright, so you can see that the blank has occurred these many times, this has occurred this many times, and so on. And how does it do it? So if you remember correctly, that the words kv basically contains the key as the word and 1 as the value. Reduce by key basically grouped all the words, okay, all the words together, and then applied your function as sum. So it's like saying group by, and aggregation function is this one. All right. So let's take this. I'll take step by step. I'm removing this. All right. So we loaded this, and let's take a peek into what is there in lines.take. We say lines.take and just first 10 elements we are trying to show. Okay, so lines.take n is this. Now you can see that there are 10 elements in this array. Each element is a line. After this we have words. Okay, words.take 10. So what does words have? Okay, words have this. All right. Basically, if you see here, what we are doing is we are taking a line, splitting it by a space, and returning all the values. Okay, and we are saying flat map. Why? Because we want to return multiple values for each value. Correct? For each line, we are returning multiple words. Therefore, instead of using map, we are using flat map. Okay, and hence it basically converted each element into multitude of elements. You can see that. Okay, next is two key value pair. We basically just put one around it. Okay, the way Tarak has asked me earlier, in the same way we have done words dot take 10. Let's just see what is there in the words KV. Okay, so you can see it here. It looks like this. So you can see that. So the one project one, so basically we have executed this function on each element. We have got this. Now the next is simply we have grouped by the key. This is the key. Okay, this is the key on which we are grouping, and then summing up all the values. That's what is done by reduce by key, and it gives us a great set of result. All right. So all right, we could say like this. All right, it has basically counted the words. Any questions here? Anitika, is it clear now? So which step is not clear to you? You can ask me now. A better way would be to ask in terms of which particular step, line number you can tell me. Okay, you can tell me the line number. Which one is not clear? I can explain. Yeah, is it clear to everyone? Which functions? The line to words. So line to words is converting the line into words, correct? And we are applying, instead of using map, we are using flat map, so that single line can return multiple elements. If you remember, in case of map, it could only return a single value. Okay, when you have to convert one element into multiple, then you use flat map. If you have to convert one value into another value, then you use map transformation, and here we are using flat map transformation. And then we have, if we have here 2kv basically appends comma 1 and puts it in as a key value. Basically it converts a single word into a key value where value is 1, and then we are basically summing it up. Alright, is everybody okay with this? Tarak, do you need any explanation here? So summing the word up is something interesting. So reduce by key is a transformation. What does it do? It basically groups all these words by key. This is the key, right? The, project, Gutenberg. It will group all of these words together and then apply your function on the values. Okay. So if 1 comma 1 comma 1 comma 1 will be summed up. Okay. So basically, it will basically, sum will be applied on all the values of that particular key. Okay. So sum is your aggregation function, and it is basically doing group by on the key. Okay. In RDBMS, the way you do group by and then apply aggregate function, this is what's happening here. And if you have, say, for a particular word there are 1000 values, then this sum function will be applied again and again on thousands of values, and then it will return the single value. Third function, which third function you're talking about? Line number, which line number? 2kv. Yeah, it basically appended. So what does it mean? It basically appends, it basically converted a word into a key value pair. Okay. Word comma 1. That's all it did. It did nothing special. So effectively, the became the comma 1, project became project comma 1, Gutenberg became Gutenberg comma 1, and so on. Okay, that's all it did. Alright, so I hope this is okay to you. Now we can save this data into an output folder using this kind of output. So it has finished saving the data. Okay, here you can have a look at it. Word count output spark. Alright, we can say Hadoop fs minus cat asgiri what? It should be there. Alright, so what did it say? Let me have a look at it. Job finished, save as text file is done. Yeah, it should be done. I just check. So Tarak's question is, so overall we are counting the number of times each word is repeated. That's correct. Our usual work, our usual example. Alright, so I hope this is clear to all of you. Now, this was the simple example. We could go ahead one more step, and we could utilize the broadcast in this manner. Okay, what we are trying to do here is, say for example, we do not want to count, we do not want to basically count the occurrence of the usual words like a and the, this, that, of, is. If we do not want to count that, we could basically use the cache, which is using the broadcast, and then we could skip it. Okay, so we have defined that broadcast here called common, and in the filter we could say that return k0 if it's not a common value. And afterwards we could also have accumulator, whose value we could keep on accumulating everywhere so that we could see the progress. Okay, this is something you should try to do. Okay, we are basically trying to utilize broadcast and accumulator in order to see the progress and also ignore the commonly occurring words. Alright, that was our Apache Spark. Any questions? Is there any built-in functions of the words like vowels and other commonly repeated words? No, I did not get your question. Is there any built-in function for the words like vowels? So yeah, we basically have defined a broadcast variable in which we have put in our values as a hash table, and then we are using that everywhere. We'll have to have our own dictionary. There is no built-in function. Okay. Alright, so that was pretty much about Spark. This knowledge is good enough to go ahead and experiment with Spark. With most of the problems which we have discussed in past, you can try to solve them using Spark. Alright. Now we have something called Spark streaming. Alright. In case of Spark streaming, so first of all, before we move on to Spark streaming, we need to understand why do we require streaming and what is streaming. Alright. So I'll give you an example of exact case where I have used streaming in past. So if we have other team member, alright, yeah. So I was hoping that one of my team member from Amazon is also attending my course, so he's also here today. And yeah, so okay, so the way we were doing streaming, I'll just explain to you. So this is clear to everybody. I can remove this. Alright, now let's understand what is streaming. I'll give you a case study first. Streaming example. So in case of Amazon, at Amazon there are many resellers. Okay, there are many resellers. These resellers keep on updating the product details. Okay, and these things keep on getting pushed into, these updates keep on getting pushed into a queue. It's a Amazon wide queue. Okay, just like event bus, we have a queue. Queue is a kind of a database which can handle concurrency parallelly from all the users. Now from this queue we had to build such that we have to read elements from the queue, okay, and then process it and find more details about those changes. So basically we have to read the changes as pushed into this queue. Okay, so okay, I think a better thing would be I can just take a not this way, we can just take a sketch. Okay, so this is say our queue. Okay, on one end there are these resellers who are pushing the these are not resellers, these are sellers. Okay, these are sellers pushing the okay, they are all pushing the changes into this queue. That somebody uploaded an image, somebody modified the title of the image, somebody changed the resolution of the image, or and somebody just updated the description. All of these keep on sending the changes, and all of these basically let me draw a queue like a queue. Okay, so this is our queue, and all the changes are going from left to right. This is our queue. These changes are going from left to right. Okay, and these all users are pushing the data there. Now we have to process this queue. So on this end we have processors. Okay, we have processors, multiple processors basically. They all process these records, and they basically consume this, and after doing so they might be pushing to some other database. Maybe say in our case there is a new system called, so we have what do you call a database. Alright, so this is the general modus operandi. So these changes are coming, imagine that these changes are coming at least 10 times in a second, okay, for argument's sake. So these processors need to basically be very fault tolerant, and these should not be operating such that that some of the processors are too overloaded, or some of the processors are very slow. Okay, so I hope this clears what I'm trying to explain. So this is called stream processing, when there's a humongous data coming from queues. So these queues are designed to tolerate a really fast number of transactions per second. Kafka, Flume, HDFS, 0MQ, Twitter can be the valid input for your for your stream processing, and the output could be HDFS database, your dashboards, wherever you want to do, and and in the between, consuming the data at such a fast pace is what is known as stream processing. Okay, so it's not equivalent of Hadoop streaming. That was totally a different concept. Similarly, streaming data in pig, that was a totally different concept. Here we are talking about consuming a lot of data at a very fast rate, and in order to consume that kind of data at a very fast pace, you might have to use multitude of computers simultaneously. So what could be the most common way? What could be the easiest way? So far people were trying to have the specialized solutions like storm processing. Okay, so earlier we were using storm. Storm is a fairly stable solution. Okay, but in case of Amazon, we actually developed our own system to process it parallelly, and that did a pretty good job. Now Spark provides you the whole infrastructure anyway. So some people realized that we could use Spark for streaming, and they wrote something called dstream, discretized stream class, which basically converts the input into individual dataset. So if you remember, our RDD was made up of elements, correct? And so some of these elements, if you look at from left to right, they could act like a stream processing. Okay, how? So whatever input data is coming from input stream, these classes like dStream provided by Spark, they will convert that into batches of data. Okay, and this batches of data will get stored as RDD in the Spark. And what does it mean? So each element will be one batch. Each element in RDD will be one batch, and the values will be stamped based on the time. Okay, so the workflow is Spark streaming receive live input data stream, divides the data into batches. Spark engine generates the final stream of results in batches. Okay, and then puts the data into database or wherever it want to put. Okay, so also please note that although everybody talks about real time, but the truth is that almost every stream processing has something called windows. Okay, everybody settles down into saying that we will operate upon one second window. Some say that we will operate on 100 millisecond window, and so on. Okay, so stream gets converted into these windows. As you can see above, the D stream, the data that is coming in, is being represented as RDD. I'm sorry. So the data that is coming in from the sources gets converted into RDD, and each element you can see that time 1, time 2, time 3, time 4, these are the individual elements of the RDD. Okay, alright, so that way you can know actually each window is an RDD. Each window is an RDD. Okay, now the next is that dStream provides you the computation on top of RDDs, and let's see that the window operations, you can see that although the data is coming at a very fast pace, we are creating the batches out of the data. Okay, and those batches are becoming the RDD at various point of times. All right, so you can see that there is an original stream which is coming in here, time 1, time 2, time 3, time 4, time 5, while the output stream is having only 3 elements. It's combining multiple elements together into a single window, right? Also, this dStream class provides us few more utility function, such as reduce by key and the window. We only had reduce by key. Here it also provides us reduce by window. Okay, so we can always say that after giving our reduce function, we could say that our window size is this much, and give us the reduced values. Okay, so those are the few elements provided by the Spark streaming. Okay, let's have a look at the end-to-end solution which built on top of Spark for streaming. Okay, so first of all, as we start the Spark streaming, we will make a connection to the data source, and while making a connection to the data source, we say that whatever is the input, convert it into this big window sizes, and that we define here in terms of duration as 1000 millisecond, which means all we are saying is read the data from the data source and convert it into 1 second, 1 second window. Okay, and after you have converted, execute our flat map this way. Okay, the way we executed flat map in case of a static data, we can also execute flat map over the window provided by Spark. Okay, in the same exact same manner. Next is okay. So basically, whatever the data is coming in into each window, we are applying flat map, meaning converting that lines into each word. Next, we are trying to do is we are converting that into key, the tuple of the word, key and the values, exactly the way we had demonstrated earlier. Next is that we are computing it here. We are basically computing the the word count using the reduce by key. Okay, and then we are collecting. Now the important part, although the whole code looks like exactly the way we did with Apache Spark, the important part here is that it's being applied only on 1 second duration, 1000 milliseconds. So we are computing the frequency of words every every second. Okay, so here we can easily give out the values. Here we can easily give out the values for for every second. So if we have to compute the word frequencies per second window, then we can use this kind of strategy. All we need to do is start the Spark streaming class, make the connection, and after we have made the connection, we start using the library provided by dstream. And once that is done, you will see that there is on one end the lines are coming, lines from 0 to 1, lines from 1 to 2, and so on. From other end, we are getting the words on each second. Okay. Alright, so this is how the streaming works. It is not different from our normal Apache Spark. The only difference is while starting it up, we have to tell that our input data has to be read from this location, and also we have to tell how big the window size we are looking for. So whatever operations that will happen afterwards will be on each window size of that much. Alright? Any questions here? So Tarak's question is, words dstream is words in a line, is it? Yes. So words dstream is a words in a window. Window could be whatever you define the size of the window. Here we have defined the size of the window as 1000 milliseconds. So basically, yeah. Yeah. So its time frame is less than lines dstream. Yeah. So it all depends on how many words are coming per second. If there are a million words coming in a second, then each window will be of 1 million words, and the RDD will be of 1 million words. Alright? Any questions still here? No questions? Nitika? Amar? Malvika? Alright, so the important thing which we need to remember in case of streaming, the whole logic is exactly like your normal Apache Spark transformation and actions. The only difference is, in case of our normal act, we were operating on RDD. Here the only difference is each RDD is basically created per second, and we operate on per second window. Great. Alright. The other solution for streaming is Apache Storm. We'll not go into the detail, we'll just compare the features. Apache Storm is a dedicated solution for stream processing. When you have so much of data to be processed by so many nodes parallelly, then you use things like Apache Storm. Apache Storm is far stable solution, and it has been benchmarked at 1 million tuples, 1 million key values per second per node, which is really fast. Per second per node, 1 million tuples is actually a remarkable performance. Okay, and it can be used with any language. It is scalable, fault tolerant, guarantees your data will be processed, integrate with queuing. Also, the important part to notice is that Apache Storm was released by, I think, Twitter. Okay, it was built at Apache Storm was built at Twitter. Okay, and it was basically done for really high performance systems. And there are machine learning, real-time analytics, and there are all other applications where Storm is utilized, and it is fairly tested at various places. Okay, so the other difference is that in case of a streaming, we process record at a time. There are batches. In case of Spark, the batches are a little bigger, and we basically handle things in the terms of batches. While the latency, meaning in case of Storm, the performance, the delay in the result is less than a second, while in case of Spark, the delay or the latency is few seconds. Okay. In case of a Storm, the record is basically processed more than once in order to avoid missing out on any record, while in case of Spark streaming, the records are only processed once. Okay, and Storm was done at Backtype or Twitter and was written in Closure, while Spark was done at UC Berkeley in Scala, and now both of them basically support Java. So the important part is the mostly what would happen is when you have already a Hadoop cluster, using Spark will not be much of a problem, and hence using Spark streaming will not be much of a problem, because for Storm you have to set up your own cluster again. Alright, so that's the downside of Spark. And sorry, that's the downside of Storm, that you have to set up everything because Storm needs its own cluster. The positive side is it has been tested for quite some time. Since 2011 it's being tested, and while Spark came through in 2013, I mean this streaming came through in 2013. So although both of the products are well supported by their corresponding teams. Okay, you can go through more details about this in this particular slide. Okay, all right, so yeah, so a lot of times we have talked about a lot of technology so far, so I'll go a little bit more into individual databases. You can have this discussion again tomorrow. All right, so a lot of times we have this question that which database to use, whether should we use Redis or whether should we use HBase, and what to use. So since there are too many choices, I will just go over it very quickly so that you build your first impression about these products. So there is a database called Redis. Redis is an in-memory database, meaning that although the data is stored onto the disk as well, but the whole data is all loaded always into the memory. and Redis runs parallelly in the network such that Redis runs parallelly in the network such that we can store complex data into Redis, and it can basically give us a brilliant performance. Okay, so the best use case of Redis is for rapidly changing data with foreseeable database size. Means the database size should be predictable and should be, we know that this kind of data is okay to have it in memory. Okay, if the data is going into hundreds of GBs, then you try to avoid Redis, because after hundreds of GBs it becomes impossible to put it in memories. Even if you have a little bigger cluster, the performance will be lower. Okay, so wherever you could use memcached, you could use it. Memcached was the caching solution for your websites. And this is to store real-time stock prices. Whenever the word called real-time comes into play, and real-time is really tough to achieve, in those cases, and your data is not too big, in those cases Redis is really good. So for complex structure of the data and for small data, but the throughput requirement is really high, in those cases you use Redis. Alright. Then there is something called MongoDB. MongoDB is best used for dynamic queries if you prefer to define indexes, not MapReduce functions. Okay. So if you need a good performance on a big database, okay, and in those cases MongoDB is good. MongoDB is especially good if your data is represented as objects, big complex objects. In those cases the MongoDB is a good solution. Okay, and if you like to create your indexes, in those cases MongoDB is great. Okay, alright. So other use case of MongoDB is that in case of MongoDB, the columns, there is not too much of restriction of columns. Okay, so if you have an older object, then basically it's easy to add more and more columns without having to worry too much. Reason being that two rows does not need to have same set of columns. Okay, therefore in those all cases MongoDB serves as a good solution. Cassandra is good for storing huge data set in almost like SQL format. Cassandra is very similar to HBase. If you have no plans to use Hadoop and you want only the database, then Cassandra could be a good solution. But if you already have Hadoop installed, if you have already a cluster dedicated to Hadoop, installing Cassandra separately would be an overkill. Okay, you could basically do everything using HBase. Okay, now HBase is great for millions of rows and billions of rows and millions of columns. If your data is smaller than 10 million or is smaller than 100 million, then you should be better with your MySQL solutions, okay, or your usual databases. Okay, so HBase is designed bottom up for really huge data. If you have, okay, if you already have Hadoop HDFS stack already, then you use HBase. Okay, so example use cases are maybe search engine, analyzing log data, any place where scanning huge two-dimensional joinless tables are required, then you use HBase. Okay, so similar to HBase, you have Accumulo and Hyper table. Okay, but if you already have Hadoop cluster, then there is no point in going ahead with any of these other solutions. Okay, so that was our a quick comparison of HBase. We will discuss the project tomorrow, and we will also discuss Uzi tomorrow. Alright? So tomorrow's class might be a little shorter one. Okay? So we'll discuss Uzi and the project tomorrow. Alright? Are you with me? Alright, so that's pretty much for today. Yeah, Tarak, can you just drop me an email? Yeah, because this session is getting recorded. So in the new session, this the one which I'm doing right now, everything that is going in the chat is getting actually recorded in the video, so that if you are looking back at the video, you don't have to worry about what's going on, what people are asking questions. Okay. Earlier, in the earlier video recordings, the questions did not get recorded, so I have to keep repeating the questions. Now you don't have to. Alright, so that's pretty much for today. That's pretty much for today. We will see you tomorrow. Alright, bye bye. Have a great day ahead. Alright, thank you very much. Bye. Bye. Bye Amar, bye Malvika, bye Huda, bye Minu, bye Nitika, bye Tarak. Alright, see you tomorrow. Have a great day ahead.